Hi, Sterling Allen here, PESN. We are at the TeslaTech Conference 2014, July 31st, and we're going to be talking with a gentleman who watched a presentation of this AuroraTek technology up in Bill Alec's room, and he saw 137% or something like that efficiency, and he knows what he's talking about from an engineering point of view, and he's going to describe what he saw and why he believes he witnessed for the first time Overunity at a TeslaTech conference. So, Brian Pinette.
Yeah, from
thank you.
Yes. So Bill Alec invited us up to his room for a demonstration, and what we saw was an array of meters, an oscilloscope, and his device, as well as a control device, just a transformer. So the first thing he did is that he hooked up the transformer, the inputs to the oscilloscope, outputs to 2 meters to measure voltage and current. Okay. And he applied I don't recall what the voltage was, a frequency, but he applied a certain voltage of a certain frequency to the transformer. And he measured the input and output voltage, the input voltage and current, taking the phase into account, which is important. Okay. And then he measured the output current and voltage on the meters.
And the phase he was measuring with an oscilloscope?
With the oscilloscope, yes. Mm-hmm. Okay. And then he calculated power for input and output, again taking phase into account on the input. For the output, he assumed the phase is 0 because that had been what it was in all of his other experiments. And that's okay, because that just means you're overestimating the efficiency of the transformer. And what he found was the transformer had an efficiency of 85%. So now he put his
That was the control.
That was control. Mm-hmm. Then he put his gizmo in place. We watched him just disconnect the transformer, connect the gizmo, same leads.
And the gizmo is circuitry? The
gizmo is, I forget what he calls it, is whatever his device is he'll be using to power his scooter. Mm-hmm. It's really an adaptation of the
Dane Hines?
Of that, yes, right, of that. So we saw, in this case, we saw a phase of about shift of, I think it was about 63% or something like that on the input. But in case we did count for phase. And then what happened, we measured the input, or he measured the input and output, the output current and voltage on the meters. And we asked him to, pardon me. We asked him to shift the oscilloscope over to the output, because even though in the past he'd been seeing a phase shift to 0, we wanted to make sure that really the phase shift to 0. So he brought very agreeable to that, he brought the oscilloscope over to the output. We measured the phase shift of the current and the voltage on the output, and in fact it was 0. So we took the phase into account on the input, and there was a phase of 0. On the phase shift of 0 on the output, it's very easy to calculate the output power. It turned out that had an output, gave you the ratio of the input to output power with 135%. So that's 35%, over unity.
And the numbers on the wattage were?
Approximately maybe about 4.9 volts input, 6.8, something like that output. Whatever comes out to 135%. That was about it. Mm-hmm. Around that. He kept the frequency, the same between the transformer and the gizmo. He had to drop down the voltage a little bit for the for his gizmo, because otherwise it would just be too much. Would have been just too much power going through there. Mm-hmm. And just kind of looking at his device, we watched just disconnect wires. Mm-hmm. Nothing else really seemed to happen between, shifting from the transformer to his gizmo. The gizmo, from the outside, was fairly simple. It looked like 3 iron cores mounted on the board. Not much room for anything beyond that. And honestly, people have asked me, well, do you think there was a hidden battery in this? And I guess what I'd say was that I just don't see how that would work in this. I didn't see any room for any other circuit or anything else in here. So at this point, I'm happy that I came to a TeslaTech conference and saw an Overunity device.
And I had a question about the, as you were describing the 135% efficiency, input versus output. Take into consideration that the transformer was 75%?
85%.
85?
Yep.
So really, it's not 35% over unity, it's 35 plus 15.
Right.
Over unity of what you would expect from a transformer that was employed in the situation.
Right. But 35% usable power, right?
Right.
So.
And then by the time you talk about usable, yeah, okay.
Yeah.
So you're satisfied, and also I wanted you to repeat kind of who was in the room and that you were kind of grilling him with questions. We were. You weren't making it easy for him.
We were making it easy for him. There were a number of people there that obviously backgrounds in EE, electronics and things like that. I did electronics as a kid. Had some introductory, had some courses in electronics in college. And I don't really practice it now, but I sort of knew about phase shifts and things like that, how to calculate this. Other people sort of understood that right off the bat. So, people were kind of asking the right kinds of questions. And I will say that he was very agreeable to just, our suggestions, trying things out. So it felt like it was an honest demonstration. I was happy with it. And
this was following the presentation he gave here at TeslaTech about the technology, the science behind it, the patents that are filed on it, and the rationale, the circuitry. And so this group that was assembled could, to a loose extent, be considered like a peer review type of crowd.
Right.
And you felt like the people who were there in the room, including yourself, signed off on it, so to speak, saying that he demonstrated to your satisfaction.
Mine.
To your satisfaction. But do you feel like the others in the room were also satisfied that?
I can't speak for them. Again, if I were going to invest money in it, I'd ask them to do it again. I'd ask them to have two oscilloscopes, maybe
at the same time,
swap them around to make sure they both have the same characteristics. I might want to actually inspect the board and things like that. But it was pretty much out in the open.
What about the calibration of the equipment? Do you feel like that you were satisfied that it was measuring things accurately?
My thought is that if there was some sort of calibration issue between input and output, it would have shown up in the transformer.
Right.
And we were seeing the transformer had an 85% efficiency, not 100 or 110. So, I'm sure the scopes in these were okay. They typically are.
Okay.
So.
Anything you want to add?
No, that's it.
Thank you.
Except that I'm just really pleased that I had a chance to see this. It was very cool.
Thank you, Brian.
Oh, you're welcome. Thank you.
Okay.
Yeah, this is how we test a transformer. And it doesn't matter if it's a standard traditional transformer like what we have here or our special transformer, there's still 4 terminal devices. So you have 2 wires coming in, 2 wires coming out.
Yes.
The input side is your power supply, which supplies a voltage and a current. AC, of course, because all transformers, they're all operating on AC. The output, of course, is our load resistor. That's what we use to power our load. And that, of course, is going to have a voltage and a current. So what we do is that to determine the efficiency of our transformer, we determine the power coming in and the power coming out to drive our load. And we do a little calculation here, and of course we determine our efficiency that way. And that's what we're going to be doing on this setup, this test setup here. So what we have over here is, of course, our frequency source, that AC frequency source, which is just a function generator. And the output of the function generator here is just wired to an audio amplifier, which then amplifies, the power. That output of the amplifier He passes, one of the leads passes into a linear current sensor, and this is what we use to convert current into voltage so we can measure it on our scope. So the scope is going to show two channels. It's going to show the voltage across our transformer and the current, okay, passing through the leads into the transformer. And what we're looking for is the phase relationship between the voltage and the current. And that's what we need to determine the input power to our transformer. So it's all part of the efficiency calculation here. Now we know that we're going to have a phase shift between the voltage and current because the input on your transformer is inductive. You know, it's just a coil of wire wrapped around silicon steel, whatever core arrangement that they have in standard transformers. Standard transformers are typically silicon steel. In my transformers, I use a better material, you know, like met glass material. And of course, the output secondary, on the secondary side, we just have a voltage and a current into this power resistor here, and that's a 25 ohm power resistor. And it does get quite warm, you know, when we run our transformer. Now, of course, transformers, they're all AC, so you need a frequency source. And this typical transformer here, it's a 60 hertz transformer, but I generally run at a higher frequency here, about maybe 1200 is what I've been demoing at. I'll just set that to about 1200 hertz. Pretty close here to 1200. That's pretty close to 1200 hertz. So we're going to measure the voltage and the current and the phase relationship. So the phase relationship, if you just do voltage times current, it gives you what's generally called the apparent power on this triangle. And what you got to do is take the apparent power and break it down into real and what is generally referred to as the imaginary component or the reactive power. And what reactive power is the power that's returned back to your source. So in other words, during a cycle, okay, a full cycle of voltage being delivered to your transformer, it's putting power in, then power out, power in, power out. That's the inductive nature of these coils. So what we're looking for is the real component side of that, and to do that you just take the cosine of the angle between the voltage and the current. Okay, the reactive side of this is merely taking the voltage times the current times the sine of the angle. But the sine of the angle is of course the power that returns back to your generator. And of course the power company, the meter on your home, only registers real power, because that's what really matters. Being delivered to your home is of course real power. And the reactive side, to load balance power coming from the power company, they generally put capacitors onto the line, which then balances between inductive and capacitance to give you that 60 hertz power component. So that's what the power company would be interested in. But for us, we're interested in of course, the real power being delivered to the transformer, to the load, so that we can determine what the efficiency of this transformer is. And we can compare that with the efficiency of our transformers.
So this is the control setup here.
Yeah. Yeah, so this will tell us everything we need to know.
And your transformer is, how does your system compare to this one here?
Well, we'll get to that.
Okay.
Yeah, we'll get to that next here. So what we'll do is we'll supply a voltage to this. The voltage shows up on channel B. And I generally run at about 10 volts. 10 volts is enough for us to get a good sample. This auto amplifier only goes up to about maybe 15 volts to test with. So we'll take this up to about 10 volts. Okay, it's right at about 10 volts, and we see we have really good sine waves, okay, coming in and out of this. And the voltage here, the B channel, of course this lower trace, this is the voltage, and then the current, okay, which is passing through one of these Honeywell voltage detectors here. It's a little Hall effect device that measures the current being delivered to the transformer, is this top trace. And you'll notice that there is a phase shift, okay, between the voltage here and the current. And inductors, the current always lags behind the voltage. So we'll see a phase shift, okay, between the voltage and the current. And that shows up as a phase shift of 17 degrees. So the scope has the capability of determining the phase shift between these two channels. Okay, so we see a phase shift of 17 degrees.
Now, as I recall, at a phase shift of 90 degrees, there's no power being transmitted at all. Isn't that how transformer works?
Well, if we just had an inductor, okay, on the primary side, and if that inductor were okay, yeah, we started here, and if the inductor was an ideal inductor, okay, the phase shift would be 90 degrees.
Ideal meaning
Okay,
no
which
resistance,
means
right?
that the top half of the power curve equals the lower half of the power curve. In other words, power is being sent to the transformer and is being sent back to the generator, such that the net gain of power is 0. Okay, it's a perfect inductor. But then, of course, no inductor is perfect. It has internal losses, little eddy currents lost in the magnetic material, also resistance in the wire, and so that'll give you a phase shift less than 90 degrees. Okay, so if we took this transformer and just unplugged the output, okay, then you'll see this phase shift increase.
It should
Now the
point out
current is
to
dropping, so I gotta boost the current. But what's happening is that you'll see that phase shift increase to about maybe 78 degrees. And it's telling you that it's just the inductive side of this transformer that is connected in this circuit. And it's not a perfect inductor by any means. So we'll see a high phase shift there. So it'll go up to about 78 degrees or so. We'll put this under load. And then when we connect a resistor to this, you'll see the primary side increasing in current. So that's very typical of a standard transformer. So we're back down to a phase shift about 17 degrees. So this is with the transformer operating with 10 volts AC at about 1200 hertz. It is delivering this amount of power to the load. So what we'll do is just write all this down. So we have a phase shift 17 degrees. The input voltage is about 10.09 volts RMS. Now RMS is very important when we do our power calculations. So we want to work with RMS.
Where are you getting that number?
Right here.
Okay.
Yeah, 10.09. So this meter is just connected across, just measuring the voltage across this transformer.
Okay.
So let's take this down a little bit. Okay. Now, to read the current, okay, from our current sensor, just switch over to the meter. So it's telling us that it is supplying a current IN of 40 milliamps
40.6.
RMS. Okay, it's an RMS value of 40.7. Okay, so we go back here.
Wouldn't you round up
So
on
right
that since
now-
it's 0.5, 0.6, so it'd be 41?
Yeah, it'd be 41. Okay, so when we do our power calculation, our power supply, it's Vn times In times the cosine, because we're looking for the real power being delivered here, of that phase angle of 17 degrees. So that is equal to, and that tells us the number of watts that we're inputting into that transformer. So that 10.09 times 0.0407, take care of that, times the cosine of 17 degrees, and that equals 0.393 watts being delivered. Now the output is just the voltage times the current, because the phase angle being delivered to a load is always 0 degrees. So V out equals 2.862 volts RMS. I out equals 0.117 amps RMS. So our load power to that resistor is 2.62 times 0.117 amps. So we have 0.335 watts. Okay? Now, to determine the COP of this system, it's just the load power over the source power. Okay, so our load, 0.335 over 0.393, that gives us a COP 335 divided by 0.3 equals 0.852. The efficiency is just the COP times 100%, which means that we have an efficiency of about 85%, which is very typical of a transformer like this. Okay? Very typical, 85%. And these type of transformers will never ever go over 100%. It's just not capable of doing that. You might get a value maybe as high as 90–95% using better components. Okay, so I'll just set that aside. Okay, now what we'll do is plug in our transformer. So I'll shut down the powers here.
Have you signed up to be on our insiders email list? Are you on it?
No.
Would you like to keep in touch with us?
Probably not by email. I have your card, so I think.
Well, he sends out email blasts to keep you up with, but when it's gonna be available for sales, things like that. So,
Okay.
Give me a moment to think about that.
sure, you can do it at the end, after you're impressed.
Okay.
That's okay, that's
Where are you
fair.
in from?
I'm from Earth, currently living in Kansas.
Oh, yeah? With
Okay,
Dorothy?
so now, you'll notice that just the general geometry of this transformer is very different than a traditional transformer. Okay, because what we have is a primary coil, okay, wrapped around two cores. And really, you have that same type of architecture in a standard transformer, this section here. Because what you do in a standard transformer is that you have the material going down the center of this coil. So really you're splitting the flux two ways, and that's what we're doing here, splitting the input flux two ways. The difference is that we have these two output coils that are wired in such a way that it has a bifilar configuration, where the output, and as I explained in my lecture, is that the output sets up opposing magnetic forces into this material. Okay, and that's very important, that we set up these opposing magnetic forces to produce an output voltage here, and it's wired, and there's two configurations available. This type of configuration here is that you can wire the output in series or in parallel, and in this case they're wired in series. And of course the ratio between the input and the output, you have about 20 turns here, about 120 turns for each secondary. So we're actually stepping up the voltage, okay, when we get to the output. So the
Question.
no load, yes.
When you said the secondaries were bifilar, does that mean these are
In its
double wound
configuration.
coils, or do you just have two?
No, they're just single wound coils, but they look like in a bifilar type configuration around this central core here.
Right, because they're both
Okay,
linking that cord.
because it looks like it's set up in an opposing configuration. Okay, you're setting up opposing forces like you would have in a bifilar configuration.
So
Because if you take a core material and then you wrap wire, double wire around it, and then you tie one of the ends together, current flows in and then it flows out, canceling. Okay, there's a canceling effect with the current flow. Okay, with the fields, well, we have the same phenomena occurring here, is that we're setting up these opposing forces.
in
Okay,
the
on
larger
output.
core there.
Yeah, and what that does to the behavior of these coils is that they lower the natural impedance on these cores, driving it over unity. Okay, where normally you wouldn't see that on an output coil here. You wouldn't normally see that. You see a fixed output impedance on this core here, on the secondary here. But on this, when this operates, the behavior is quite different. Okay, because we have this cancellation going on, lowering the impedance on
Do you care
these
if I take a
coils.
photo of that?
Yeah,
Is
go
it okay
ahead.
to take a picture of that?
So your two secondary coils are effectively in opposition to each other.
Exactly.
Because they're linked with
And
the core.
that's a key feature with building over unity devices, because we're actually lowering the output impedance on these coils.
I noticed that the resistance is different in those two. Is that intentional, or is that within a
Well, it's
range?
just what happened to work out.
Okay.
You know, when you wind these coils,
So it seems to me the textbook analysis would say that, you know, the two fields of those second.
there is something going on. There's another force involved, and we'll show that here. Okay? Okay, now this coil arrangement here operates at a higher frequency, more optimum and that standard transformer. I typically run this transformer at about 3200 hertz. Gives me about the best performance. So we're just about there at 3200 hertz. So let's apply power. Okay, so right away, with this running and under load, we see that we have a very high phase angle, okay, between the voltage and current. It's much higher than a standard transformer. So let's take that up to 10 volts. Okay, so we see a phase angle of about 74, it's between 74 and 78, kind of bouncing around between the two. The scope does an approximation. Okay, 7481. Okay, so we'll just go with that value there. The scope is doing an approximation with the number of cycles. Calculating with
074,
that phase.
is that the phase angle?
That's the phase angle, 74
reading
degrees.
is-
The standard transformer, we saw a phase angle about 17 degrees. So here we're way up there. So we're saying that the input side here is highly reactive. Even though we're driving a load with it, the input side is very reactive, much more so than a standard transformer. So that's the first big difference that we see. So we have phase angle. Now it's kind of, the scope is kind of rough here. So we'll just say between 74 and 81. We'll just use
split the
maybe
difference.
78 degrees, let's say. So the VN, 10.75 volts RMS, IN. Our input current is substantially higher, 1.466 amps RMS. Okay, so our power, our source power that's being delivered, let me do this calculation, 10.75 times 1.466 times the cosine, 78 degrees. We see that we're supplying to this device 3.277 watts of power. Our output, V out, is at 11.39, and I out equals 0.459 amps. Okay, so our load power works out to be 11.39 times 0.459.
Are we assuming again the phase
Five.
angle is 90 degrees there?
So
0.
Or 0 degrees, I'm
Yeah,
sorry.
because
yeah,
we're
0
driving
degrees.
a resistive
Yeah, okay.
load.
Okay, you got it hooked on a resistor. I see.
Yeah, I was showing
Hooked on a
people
resistor there.
yesterday that the phase angle was indeed 0 degrees.
Yeah,
So
I
we
talked to a
got
guy who attested to that. You put the oscilloscope on the output and it did show 0.
Okay, so right away we see 5.228 watts on the output, and the input is at 3.277 watts. That when we do our COP calculation, okay, so it's 5.28 divided by 3.277 equals 5.228 divided by 3.277.
That's neat. I like that.
Okay, 1.596, or an efficiency
160%.
Pretty awesome.
of just about 160%.
I like that.
Wow.
So you're gaining,
That's
okay,
cool.
so you're charging current or power
Yeah,
to
we're
charge your
putting
battery is
real
about a 2-watt
power
extra.
at that phase angle is saying that power's coming in, power's coming out, because it's highly reactive. All right? But the real power that's being consumed by the device, okay, and supplying power, plus power to the load, all right, it's only 3.277 watts. But yet our load is telling us that we're dissipating 5.228 watts.
Can I touch those resistors?
Oh yeah,
Yeah, they're warm.
warm, huh?
Ouch, hot.
Oh,
almost
yeah.
almost burning hot.
Yeah, it'll melt that plastic.
Turn it off before.
Okay, but I'm going to show you something here that is really amazing. Okay, it's not done yet. Okay, so we're showing here that the efficiency of that transformer is up 160%, which is unheard of. Okay, in the mainstream world. So now what we'll do? Okay, now what I got to do is turn everything back on again because it times out on me. It's back on. Okay, so we're supplying this voltage at the current value here. Now keep an eye on this, okay, that
Yes.
phase angle, because what I'm going to do is now take the output of this and short it. Okay, I gotta turn this down a little bit because it pulls too much power. So we'll keep it at a lower power. But look at that phase angle now. Since I shorted the output on this device with this current, boost it up a little bit here. That phase angle is over 90 degrees, 102.
Can
And
we
you can
take these?
actually
Can we
see it.
record these measurements and calculate the input versus output?
Yeah, because what we can do now is that since this is shorted to maximum current over there, we can now look at the power over here. We see that we're supplying, we can boost that up a little bit, increase the power. Okay, so let's say that we're at 8 volts in this case. So let's supply, our supply here is 8.09 times, let's see what that current is. That current is at times 1.216 amps, okay, times the cosine of that phase angle. Cosine of 102 degrees. So we're supplying here, it's telling me that it's negative 2.04 amps.
Watts.
2.5, excuse me, yeah, you're right,
yeah,
watts.
Yeah.
2 watts negative 2 watts are being sent back to the generator. 2 watts.
Because of the 92 degrees.
Because we're over at 90 degrees. And you can actually see that on this meter. Okay, on this scope. So what I'll do is expand this out.
So in other words, it's sending power back to your power supply.
Exactly. And that, if you look closely here, what I'll do is move this over. Now the 90-degree mark is where we intersect, is our 0 line. Okay? And if you look closely here, you'll see that the peak of the current is past the 90-degree mark. So yeah, we're getting a good reading. It's over 100 degrees. It's over 90 degrees. So that means that the cosine of anything over 90 degrees is going to be a negative number. So it's telling us that power is actually coming back. We're supplying power to the transformer. It's returning back reactively here. But what that says is that the peak, you look at the power here, the area under that curve. The curve that is being sent back to the generator is greater. Okay, that curve is going to be greater. You're going to have something that looks like this. Okay, where in a standard transformer, you're always going to have something that looks like this. All right. Now at 90 degrees, they're perfectly balanced. Whatever you put in, you get back out. You're 100%, you know, the net gain is 0. But for a standard transformer, you're going to have a curve like this, where you have to put more power in than what you get out. This efficiency is always less than, it's always less than 100%. But our transformer, it's sending back more power than what we put in. This is what's so extraordinary about this device.
And the output is 1.2 times 0.386.
Yeah, well, the output is just putting out this maximum current here. That voltage, it's just looking at just a little bit of voltage, probably the drop in the wire is what it's looking at there. But the maximum current there is only 386 milliamps. So you're not going to destroy the device. All right. As a matter of fact, the device, unlike a conventional transformer, this device here runs cooler. It starts to cool down rather than heat up. So we can take a temperature measurement here. Let's look at that. We see a 73.2. Okay, 73.2 degrees. Go and measure this guy. 72.5. So it's running cooler, you see.
So this was 73.2 and that's 72.5?
Yeah, we'll do this again. We look at that surface, 73.2. We look at this white surface. And Graham Gunderson told me to do it this way. 72.5. It should be running hotter.
Yeah, after being shorted for 5 minutes or so.
Yeah. So the device is running cooler. So what are we dealing with here? We're dealing with some sort of source that's all around us here, some sort of a negative energy. And that's what's pushing this waveform beyond 90 degrees. Now there's another force at play here. This other force acts like a negative electromagnetic force that's acting on the current, pushing it beyond 90 degrees. So yeah, I mean, you can actually see that shift in that curve there. Because when we cross the 0 point on the voltage, you then move your line up to the current, and you see that the peak is over 90 degrees, which is extraordinary. So, that is the demonstration.
Thank you. Right, right.
So,
And then by the time you talk about usable, yeah, okay.
Yeah.
So you're satisfied, and also I wanted you to repeat kind of who was in the room, and that you were kind of grilling him with questions. You weren't.
We were.
You weren't making it easy for him.
we were making it easy for him. You know, there were a number of people there that obviously backgrounds in EE, electronics and things like that. You know, I did electronics as a kid. You know, had some introductory, had some courses in electronics in college. You know, and I don't really practice it now, but I sort of knew about phase shifts and things like that, how to calculate this. Other people sort of understood that right off the bat. So, you know, people were kind of asking the right kinds of questions. And I will say that he was very agreeable to just, our suggestions, trying things out.
Mm-hmm.
So it felt like it was an honest demonstration. I was happy with it.
And this was following the presentation he gave here at TeslaTech about the technology, the science behind it, the patents that are, filed on it, and, the rationale, the circuitry. And so this group that was assembled could, to a loose extent, be considered like a peer review type of crowd.
Right.
Mm-hmm.
Okay.
And you felt like the people who were there in the room, including yourself, signed off on it, so to speak, saying that he demonstrated to your satisfaction.
Mine.
To your satisfaction. But do you feel like the others in the room were also satisfied?
He measured the input and output, the output current and voltage on the meters, and we asked him to. Pardon me. We asked him to shift the oscilloscope over to the output, because even though in the past he'd been seeing a phase shift to 0, we wanted to make sure that rid of the phase shift to 0. So he brought very agreeable to that, he brought the oscilloscope over to the output. We measured the phase shift of the current and the voltage on the output, and in fact it was 0. So we took the phase into account on the input, and there was a phase of 0. On the phase shift to 0 on the output, it's very easy to calculate the output power. It turned out that had an output, gave you the ratio of the input to output power with 135%. So that's 35%, over unity.
And the numbers on the wattage were?
Approximately, maybe about 4.9 volts input, 6.8, something like that output. Whatever comes up to 135%. That was about it.
Mm-hmm.
Around that. He kept the frequency, the same between the transformer and the gizmo. He had to drop down the voltage a little bit for the for his gizmo because.
Hi, Sterling Allen here, PESN. We are at the TeslaTech conference 2014, July 31st, and we're going to be talking with a gentleman who watched a presentation of this AuroraTek technology up in Bill Alec's room, and he saw 137% or something like that efficiency. And he knows what he's talking about from an engineering point of view, and he's going to describe what he saw and why he believes he witnessed for the first time Overunity at a TeslaTech conference. So, Brian Pinette.
Yeah, from
thank you.
Yes. So Bill Alec invited us up to his room for a demonstration, and what we saw was an array of meters in a oscilloscope, and his device, as well as a control device, just a transformer. So the first thing he did is that he hooked up the transformer the inputs to the oscilloscope, outputs to 2 meters to measure voltage and current. Okay. And he applied I don't recall what the voltage was, a frequency, but he applied a certain voltage of a certain frequency to the transformer. And he realized it would just be too much. The different would have been just too much power going through there. And just kind of looking at the device, we watched just disconnect wires. Nothing else really seemed to happen between, shifting from the transformer to this gizmo. The gizmo, from the outset, was fairly simple. It looked like 3 iron cores mounted on the board. Not much room for anything beyond that. And honestly, people have asked me, well, do you think there was a hidden battery in this? And I guess what I'd say was that I just don't see how that would work in this. I didn't see any room for any other circuit or anything else in here. So at this point, I'm happy that I came to a TeslaTech conference and saw an Overunity device.
And I had a question about the, as you were describing the 135% efficiency, input versus output. Take into consideration that the transformer was 75%?
85%.
85?
Yep.
So really, it's not 35% over unity, it's 35 plus 15
Right.
over unity of what you would expect from a transformer that was employed in the situation.
Right. About 35% usable power. Right. Measured the input and output voltage. The input voltage and current, taking the phase into account, which is important. Okay. And then he measured the output current and voltage on the meters.
And the phase he was measuring with an oscilloscope?
With the oscilloscope, yes. Okay. And then he calculated power for input and output, again taking phase into account on the input. For the output, he assumed the phase is 0 because that had been what it was in all of his other experiments. And that's okay, because that just means you're overestimating the efficiency of the transformer. And what he found was the transformer had an efficiency of 85%. So now he put his
That was the control.
That was control. Then he put his gizmo in place. We watched him just disconnect the transformer, connect the gizmo, same leads.
And the gizmo is circuitry?
The gizmo is, I forget what he calls it, is whatever his device is he'll be using to power his scooter. It's really an adaptation of the
Thane-Hines?
Of that, yes, right, of that. So we saw in this case, we saw a phase of about shift of, I think it was about 63% or something like that on the input. But in case we did account for phase. And then what happened, we measured the